Hey everybody, Vade here. A student that has been working with me has given me this problem, and I kind of found it pretty interesting. I've done this problem before when I had studied pre-calculus slash intro to calculus. Of course, because limits are technically in calculus, but they are covered in various pre-calculus curriculums. And what I really like about this problem is that it introduces you to position, velocity, and acceleration, specifically how it intertwines with calculus, right? Now, when you study derivatives, and derivatives come from limits, you will see how, for example, derivative of position is velocity, derivative of velocity is acceleration, and if you really want to go further, the derivative of acceleration is the jerk. And if that means nothing to you right now, it should mean nothing to you because you're right now at limits, you're not yet at derivatives. Um, it's going to be crucially important, and it's also a really good way to just understand what the significance of the derivative instantaneous rate of change. But again, this problem just kind of serves as an introduction to just position, velocity, and acceleration in mathematics. Now, you've probably already done maybe a velocity problem before you even started calculus, yet alone limits, right? Think about how if someone throws a ball in the air and how that can be modeled through a quadratic function, you can actually use that function to find when the ball hits the ground, of course, using finding the roots of that quadratic equation, right? So that's an example of a problem that you've probably done already, and if not, that's fine because we're going to be doing it in this problem anyway. So we're given the position function. Now, position function is usually always denoted as s of t, okay? Now, sometimes this may just be implied, right? You may just be given s of t, so just assume it's the position function unless otherwise specified. So we're given that s of t here equals to negative 16t squared plus 500. It gives the height in feet of an object that's fallen for t seconds from a height of 500 feet. Okay, and this should all make sense because the height, right, is the 500 feet here, which is the initial, which is right here. So hopefully that makes sense. It's just giving context to this equation here. But again, problems like this don't always give you the height of 500 feet. You just have to know it based off of the constant here. Okay, and the velocity, the velocity at time t equals a seconds is given by limit as t approaches a of s of a minus s of t over a minus t. Now, what's quite ironic about this, and again, you haven't gotten to derivatives yet, but this is actually called the alternative form of the derivative, or the alternative definition of the derivative, because you're trying to find this. This gives you the instantaneous rate of change at a point. Now, if you're aware of the difference quotient here, it's just another way of representing the difference quotient, but then you have a limit. And again, I'm not going to get into details, but this essentially can help you find the derivative at a point. Okay, now you may not know it yet, but this is what you're doing. Okay, you're using the alternative definition of the derivative. Okay, so I'm going to rewrite this here. The limit as t approaches a of s of a minus s of t over a minus t. Now, using your knowledge of limits here, if we, of course, directly substitute a, I'm going to draw a thought bubble here. This is what I've been doing recently. And again, you don't want to like just do, you don't want to necessarily equate this to the direct substitution if it's in an indeterminate form, because that may not be mathematically correct notation-wise. So just put it in a thought bubble. And this is very important, especially in AP Calculus. You want to make sure that your AP reader is aware of what you're thinking about and that there are no linkage errors. So if we do this here, we directly substitute a into this. We get s of a minus s of a over a minus a, and hopefully you realize that that's 0 over 0, which is one of our many indeterminate forms. So what we can do here is we can do some sort of algebraic manipulation. So we're given s of t here, and I'm going to rewrite it here. S of t equals to negative 16t squared plus 500. If we want to find s of a, it's just as simple as plugging in a in for t. So s of a will equal to negative 16 a squared plus 500. So what we'll get here is the limit as t approaches a of, what did I write here, negative 16 a squared plus 500 minus s of t, and again s of t is negative 16 squared, negative 16 t squared plus 500. And again, this may not seem like oh, what's the point in writing this? This is not going to change anything. Well, just wait, and then we're going to have this all over a minus t here. And just to save space here, I'm going to rewrite the limit as t approaches a of negative 16a squared plus 500 plus 16t squared minus 500 over a minus t. And these 500s will cancel, and we're left with, can put an arrow here, we're left with the limit as t approaches a of negative 16a squared plus 16t squared over a minus t. And then what I'm going to do here is I'm going to factor out the negative 16 here. So I'm going to do negative 16 times a squared minus t squared. Now maybe you're seeing, you can see it right away what will actually be happening here, but just give me a moment here. So over a minus t, I'm going to use one of our many properties or limits here and take this 16 outside of the limit. Since it's a constant, it won't change our result if we take it out. So we'll get negative 16 limit as times the limit as t approaches a of a squared minus t squared over a minus t. And now I'm going to draw another arrow here. And hopefully you realize here, a squared minus t squared, difference of two squares formula. So now, if you weren't aware of it earlier, now you are. So this will then be limit negative 16 times limit as t approaches a of a plus t times a minus t over a minus t. And now a minus t will cancel, and we are now left with negative 16 times the limit as t approaches a of a plus t. So now we can directly substitute here, because obviously we won't get an indeterminate form by plugging in a in for t, so then we'll just get negative 16 times a plus a, right? We're directly substituting this a here into this t, okay? So then we'll get negative 16 times 2a, which is negative 32a. So now if we go back to the problem here, it's saying how fast will the paint can be falling after 2 seconds. So remember, a is seconds, okay? So 2 seconds means we plug in 2 in for a. So then we'll get negative 32 times 2 equals negative 64. Okay, so now we really need to answer, with context here. Okay, this is very important because it shows that we really understand what's going on, of course, in the real world, outside of this largely theoretical world of mathematics. So we have this negative 64 here. Remember, this is height in feet. This is time in seconds. So this is going to be negative 64. We're going to have negative 64 feet per second here. So I'm going to draw a side bubble here. Right, so it'll be negative 64 feet per second. Okay, so there are two ways to answer this here. Okay, there are two ways. So the first, we can say A, right? This is the easiest way of doing this. Is the paint can is falling at a rate of negative 64 feet per second. Okay, so this is the easiest way of doing this here. Okay, the paint can, or actually no, this would not be really correct. The paint can is moving. Okay, moving. Okay, and then B here would be the paint can is falling at a rate of positive 64 feet per second. So let's talk a little bit about velocity. So velocity is not like speed, okay? Speed is the absolute value of velocity. Speed is always positive, okay? Speed is always positive. You're not going to see the speedometer of your car and say, oh, I'm going at negative 35 miles per hour right now. That's not how it works with speed. But unlike speed, velocity, right? Remember, speed is the absolute value of velocity because speed needs to be positive and absolute value always yields a positive output. Velocity is actually based off of direction. So based off of the context here, if you're going up or to the right, your velocity will be positive. And if you're going down or to the left, again, my left and your left and my right and your right may be different, but you get what I mean. If you're going down or to the left, your velocity will be negative. Okay, so if you think about this here, this is falling object. Okay, so we're falling, so we're going down. Okay, so we're going down, our velocity is negative, and that is expected because we got the negative 64 right here. Okay, but now we just need to interpret it. Okay, so it would be incorrect, like I almost did here. The paint can is falling at a rate of negative 64 feet per second. Okay, this is just not correct because falling is negative. Okay, like think about falling. This word itself carries like a negative sign almost, like this is negative right here. And then if I put a negative 64 here, this would be negative of a negative, and then that would be positive, and that would just not be correct. Okay, because the paint can is not going at 64 feet per second, it's going at negative 64 feet per second. Okay, so that's just, the translation is wrong. Okay, but moving here, moving implies that we're going up or down. Okay, so it's really like ambiguous, right? So, but to remove that ambiguity here, we'd say negative 64 feet per second, so that means we're falling. Okay, so that's why you got to be very careful here with interpreting your answer. Think about what's going on in the real world is my best piece of advice, right? Like it tells you, it's giving you more than it really needs to, but that's really good. It's a falling object. It's falling. You're dropping a paint can. Okay, it's falling, and it's modeled by a position function. So, all right. Hopefully that makes sense here. All right. So now we have 102, and this one is probably a problem that you could have done in Algebra 2 or Algebra 1 even. Okay, so a construction worker drops a full paint can from a height of 500 feet. When will the paint can hit the ground? At what velocity will the paint can impact the ground? So let's first do the first part. So full paint can from a height of 500 feet. When will the paint can hit the ground? 500 feet. Our constant in the given equation was 500. And this is negative 16t squared plus 500. So for the first part of 102, right, I'm going to label this as 101. Okay, 101. For 102, right, 102, and this is part A, we literally just solved the quadratic equation here. Now, again, this is my first time doing this problem. I'm just looking at it here. So you just set this equal to 0. Now, I'm not gonna actually answer this. I'm not gonna solve it on video because it's just too foundational of a skill. I'm just gonna skip that. I mean, we could do some of the work. Negative 16t squared equals negative 500. T squared equals 500. over 16, t equals plus or minus the square root of 500 over 16. Okay, we can interpret that in the context, okay? So, first of all, we got plus or minus here. We got plus or minus. Okay, so first of all, when? So when will the plant hit the ground? So this is time. Okay, this is time, right? We solve for t. T is time. And time is always positive. There's no direction with time. That's just, no, time is always positive. Okay, time is positive. So this right here, the negative root would not count. So this would just be, the time would be, I'm going to write a thought bubble here. It would be, again, I'm not simplifying this here. We could do like square root of 500 over 4. I'm not going to do any more radical simplification here. Seconds. Okay, this is our unit of time, right? Because it's giving us seconds, so seconds, right? So we got t equals square root of 500 over 4 seconds. So now we need to interpret this in the context here. So when will the paint can hit the ground? So we can say, and this is again very straightforward response to that application here. We can say the paint can hits the ground. And again, you should probably put this into a calculator and get some decimal answer, just so it better suits the application. But again, I don't have a calculator with me right now, so I'm just going to deal with what I have. Put that in a calculator. And if you don't, you're not allowed, if you are not given a calculator, just leave it as is, or simplify the radical. Do as you are told in instructions. So anyway, hits the ground at, we can say when t, right, t equals to square root of 500 over 4 seconds. That's totally acceptable. Okay, so we just answered A. So B is what velocity, okay, what velocity. So first of all, velocity, we think about this limit here, which gives us velocity. Okay, if you guys don't know derivatives yet, I'm trying really hard not to expose the secrets of this and how it can be done in like I could do this problem in like maybe 5 seconds. Not 5 seconds. Like hypothetically, like 30, like 1/4 of the time it took to do this, knowing derivatives and derivative rules, because this is a derivative at a point. But just understand that velocity, this is derivative of position is velocity. You'll get more into that later, but it gives us this. It gives us this limit to find velocity. So pay attention here. So at what velocity will the paint can impact the ground? Okay, so we need to understand here that we need it to be at this t here. We need to use this t value here in order to do this. So A equals to the square root of 500 over 4 seconds, right? So we can do limit as t approaches, so what we can do here is then just use our expression of negative 32a, right? We had that expression here, the negative 32a feet per second. We can just plug in this here, so we can have negative 32 times square root of 500 over 4 seconds, or feet per second. So now, again, 2 ways to respond to this. We can say here that velocity, the paint can will be moving at, and again, this is instantaneous rate of change, what derivative is, so it's like at, what is the velocity at that instance, so that's what the derivative is, slope at a point, tangent line, maybe you may hopefully know tangent lines from geometry. Anyway, this is answer choice A here. I'm not going to simplify, well, we can be a little pleasant here, we can rewrite it as negative 8 square root of 500 feet per second, right? So we can say that the the velocity of, or we can say the velocity. Yeah, we actually don't need to have multiple answers. We can just put one because it's just we can literally just directly answer the question. The velocity of the paint can at the instance it hits the ground is -8 square root of 500 feet per second. And so that's our answer. So hopefully you understand this here. Thank you for being patient here. Sorry if I made any mistakes, please let me know. But yeah, see you guys on the next one.